Hello, this video is going to introduce us to collisions. We're going to do this in a simple way with collisions going in a straight line to start off with. And one we know about quite a lot is about snooker balls. So a snooker ball, I hit a snooker ball here in that direction and it bumps into a stationary snooker ball there. Well, what happens? Well, in practice we see this one comes into third and that one goes shooting off, doesn't it? If this is our cue ball on the left and the ball we hit goes shooting off quite fast, doesn't it? Afterwards the snooker ball, the cue ball, tends to sort of travel on quite slowly, doesn't it? That's what we experience, that's what we normally see, and we're going to work out why that happens by looking at the maths of it. And the most important thing is that this is all a function. The first function is around momentum. And what happens to momentum? Well, in the past, we've already derived some rules, haven't we? That momentum is mv. And we also found out about a thing called an impulse. So an impulse is a force times the time of a body, and it results in a change in the momentum of that body. And we're going to use that for the first half, and then we're going to introduce a new law or experimental law that Newton found, and we're going to put the two together and it's going to show us how the maths works. So looking at the impulse and change of momentum, impulse equals change in momentum. That was our fundamental idea. So the first thing we need to do is start thinking about what happens when two balls collide. So I've got a more general case now, two balls bumping into each other. What happens is there's an impulse between the two balls, for a short period of time, isn't it? It's probably quite a very short time, less, 0.1 of a second or something, and there's can only be one impulse, and it's the same, it's equal and in opposite directions, isn't it? It's like action and reaction. It's the impulse going between the two bodies. So on my left hand body, I'm going to set this up so we can see it. I've got my before velocities on the top and I've got my after velocities on the bottom. So beforehand, the left hand ball is traveling at velocity u1 in the right and going to the right, and the right hand ball beforehand was traveling at u2 going to the right. I've made all the velocities travel to the right at this point because that makes life easy for us and it helps us see what's going on. And afterwards they're traveling at v1 and v2 to the right. And what happens between the before and after is we get this impulse. Well, we can use the impulse equals change of momentum law to look at what happens. So let's have a look at the left hand ball, and we're doing all our calculations traveling to the right. So for the left hand ball, the impulse is a negative I impulse because it's to the left, and the change in momentum, well, it's the v1 beforehand minus the v2 afterwards, isn't it? And if we look at the right hand ball, well, the impulse is to the right, so it's speeding it up, and the change in velocity, so change in momentum, is the v2 minus the u2 times m2. Okay, so if we equate the i's from those two formulae, we get the left hand side, but we get a negative of the left hand side, equals the right hand side. Now I'm going to rearrange this because it's really important. And on the left hand side, I'm going to pick out and put all the momentums from the before situation. So which one have I got there? Well, I've got an m1u1 here. That's the momentum of the left hand ball. And over here I've got an m2u2. It's negative on the right hand side, so when I move it over it becomes positive. So what I've got here on the left hand side is the momentum before. If I then look for the momentums afterwards, I've got an m1 v1. It's negative when it's on this side, so when it changes, I move it to the other side, it's positive. And I've got an m2 u2, sorry, v2 there, which is the momentum of the right hand ball afterwards. So what have I proved here? Well, I've proved that the left hand side, which is the momentum before, equals the momentum afterwards. So in one of these collisions, because we've got a single impulse, we've got conservation of momentum, and that always takes place. There's always conservation of momentum because we've got a single impulse and it's the same impulse. Okay, now we need something else to help us solve these problems, and Newton did work on this, and so he created this law, which in Edexcel you're going to see called Newton's law of restitution. Sometimes you'll also see it as Newton's experimental law. So if I take this ball here and I just drop it, it bounces off the floor. Quite often it doesn't bounce up to the original height, does it? So Newton investigated this, and he came up with a law that if he took this ball and that piece of floor and he dropped it from different heights, what he found was there was a constant ratio between the speed of separation, which is this bit here, how fast the ball moves off once after the collision or the bouncing off the ground, and the speed of arrival, which is the speed that hits the ground at, yeah? And usually the speed of separation that it goes up is going to be less than the speed it goes down, yeah? That's what we see in our in real life, isn't it? And he found that these two, if you just did loads of experiments and divided one by the other, you've got a constant ratio, and this thing's called the coefficient of restitution, and it's called coefficient, and it has a range between 0 and 1 for reasons we probably will understand. So let's follow our way through. If we had something like an egg and we dropped it, it would just go bang and it wouldn't come up at all, would it? So our speed of separation would be 0, so we wouldn't get a bounce, and that's an extreme position, isn't it? Don't see that very often, but it will happen with things like eggs. So in that case, E would equal 0, yeah, because it wouldn't go away at all. It wouldn't bounce, it would just land and go dump. You see the same thing with jugglers' balls, don't you? If you ever use those, they hit the ground, they go dunk. That's it. So E equals 0, we get no bounce, and this is called totally inelastic collision. At the other extreme, we get a super bouncy ball, one of those sort of super balls, and they're going to bounce up as high as we drop them. So in that situation, the speed of separation equals the speed of arrival. E will be 1, we'd get a full height bounce, and this would be called a perfectly elastic collision. We can't really go out faster than we came in because that means creating energy. So those are our two extreme positions, and that's why our E value, our coefficient of restitution, must be between 0 and 1. Really important. I'm going to pause just a moment so you can think about that. Okay, so I've now got two rules, and the question for us is, particularly looking at that latter one, is that work that Newton did with a ball hitting the ground, how does that relate to two balls bumping into each other? Well, if we use the sort of setup we did earlier, how are we going to interpret speed of separation and speed of arrival? Let's start with speed of arrival. Well, if this ball's coming in at U1 and that one's going in at U2, you'll note that I've changed direction, and I've only done this in this example to make it clearer for you, because on everything else they'll all be going the same direction. We could see here that if that one's coming in and that one's coming in, that the speed of arrival, they are coming together we add them together, don't we? U1 plus U2, because it's like two cars driving towards each other, isn't it? So that's U1 plus U2. And then the speed of separation, well, if this one's going away at V1 and that one's going away at V2, we can probably see that the speed of separation is increased, isn't it? There's V1 plus V2. So I just want to get that idea in your heads. Yeah, then what we're trying to do is work out how fast they're coming together for the speed of arrival, and then we're having the speed of separation is the opposite. And Newton found that this law applied in that situation as well, equally well if we use speed of separation and speed of arrival as we've just described. So I'm going to give you a couple of examples here, take us through the two extreme examples for that. Okay, I'm going to start with a snooker ball. I've got a cue ball here on the left, and I'm going to hit that into a static ball on the right. Yeah. So as I said before, I'm set up my before and after velocities. So my before is u in this direction and 0 for the right hand ball. I'm having all my velocities going in the left to right because it's important when we do the maths, and you will have that most of the time. Now after the collision, I'm assuming that the left hand ball, the cue ball, is going at V1 and the target ball is going at V2. So as we saw earlier, we're going to have conservation of momentum. So on the left hand side, when I start substituting in values, the left ball's got momentum mu, and the right hand ball has no momentum, it's m times 0. And afterwards I've got mv1 plus mv2. Now you can see m is a common factor here, so I can cancel that out, and so I know that v1 plus v2 must equal u. That's my first equation. Now I've now got to use the law of conservation, there's law of restitution. So let's just have a look. So what I need to calculate is my speed of separation and my speed of arrival. So let's have a quick look at our board. Well, this speed of arrival is pretty straightforward, isn't it? This one's traveling at u, and that one, the right hand one's traveling at no speed at all. So my speed of arrival is u minus 0, isn't it? Which is going to be u. Yeah. What's my speed of separation? Well, afterwards, this ball's traveling at v2, but this one's traveling in the same direction, so they're actually so the speed of separation is reduced, isn't it, if they're both traveling in the same direction. And v2, the speed of separation is going to be v2 minus v1. Of course, we'd expect v2 to be greater than v1, otherwise they wouldn't separate. So v2 minus v1. So speed of separation is v2 minus v1, speed of arrival is u minus 0. And if I just take this equation, of course, that effectively that we can ignore that there. So I've got v2 minus v1 over u. If I multiply up by u, I've got second equation, v2 minus v1 equals u. Okay, so I've got two simultaneous equations here, v1 plus v2 equals u, and the second one is v2 minus v1 equals u. If I add those two equations together, I'm going to get 2v2 equals 2u, so I can see v2 equals u. And if I subtracted the bottom one from the top, I'd end up with 2v1 equals 0, because u would be u minus u. So that means that my v1 is 0. So if I have a quick look at that as a diagram, as a result, what's it telling us? Well, this ball came in at speed u, and that ball went out at speed u. This ball started at rest, and the incoming ball ends up at rest. So all the momentum was transferred from the left-hand ball to the right-hand ball. Now that's what we roughly see in snooker, isn't it? That nearly the ball, the target ball, goes shooting off, and the cue ball doesn't move at all. And that's because in snooker, E is about, on snooker balls, E is about 0.96. So we're quite close to this situation. There's something else for us to look at in this situation, and let's have a quick look at energy. So this ball came in with speed, kinetic energy, because there's only one sort of energy we've got here, that's kinetic energy. There's no potential energy or anything, they're all on the level. Yeah, so if we look at the kinetic energy, well, this one came in, the cue ball came in with kinetic energy half mu squared, and the target ball went out with kinetic energy half mu squared, and the other there was no energy in the other ball before and after. So if and only if we can see that we have this situation of a perfectly elastic collision, we actually get conservation of energy as well. Yeah, half mu squared before, half mu squared afterwards. But that's the only situation. If and only if there's a perfectly elastic collision, we get conservation of energy. Quickly look at the second example. Let's have a totally inelastic collision between our snooker balls, so E equals 0. Well, same setup as we had before, nothing different. Conservation of momentum's the same as before, so we get the first equation the same. V1 plus V2 equals 0. What changes is afterwards. The right-hand side of our law of restitution is the same, yep, still V2 minus V1 over U minus 0, U minus 0, that's right. On the left-hand side, now E equals 0. So all I need to know now is that V2 minus V1 equals 0. So here are my two equations, simultaneous equations. If I solve those, I find that V2 is a half. Yeah, if I just added those two together, I'd get rid of the V1, wouldn't I? And I'd have a U on the left-hand side, 2V on the left-hand side, sorry, 2V2 on the left-hand side, U on the right-hand side. So V2 equals a half U. And because V2 equals V1, V1 equals a half U. Here we go. So if I look at my final setup, this ball came in at U, and both of them go out at the same speed of a half U. So they're effectively going out side by side, yeah? And that's called coalescing. You'll note as well that we haven't got conservation of energy here. Okay, so there we are. This is the summary for you to look at. We've always got conservation of momentum. If we've got fully elastic collisions, we're getting conservation of energy. If we haven't got fully elastic, we're going to have collisions, we're going to have to use Newton's law of our restitution, and we need to know a value of E. Hope that's of use.